All right, we just finished up the phosphoglycerate mutase, or PGM, reaction, and we pointed out that that is an isomerization. And that's an isomerization where we break a phosphoester and create a phosphoester. So we said that that is energetically a wash. Now, let's make sure you understand that mutases have a general idea about them. Let's go to that page where we were filling in these types of definitions. Mutases in general are going to be enzymes that move a phosphate group within a molecule. Not from molecule to molecule, that would be group transfer, that would be a kinase. In this case, it's within one molecule. Now, I do have to tell you that when we say it's a phosphate moving, it actually can be a lot of different types of groups moving, but in this class, it's pretty much always going to be a phosphate, so we'll leave it at that. Okay, let's get back to where we were in glycolysis, and as always, we're going to pick up where we left off. We created 2PG, now we've got to do something with 2PG. This is kind of a tough reaction. And this is going to be reaction 9. It's an enzyme called enolase. And I'm going to go ahead and write out the name of the product here for you. It's called phosphoenol pyruvate. None of that really works very good chemistry-wise, except for the part about the enol. We'll come back to that in just a little bit. Here's a practice for you. I want you to start to think like a chemist. And one way we can do that is to look at the substrate and look at the product and ask what has changed and what do you expect has to happen to make this change occur. So pause it for a minute, look really carefully substrate to product, and see if you can predict what type of chemistry we're going to do here. Okay, the key for this kind of work is to look for the difference. And everything's the same except we get rid of this alcohol, see it's no longer here, and we go from a single bond to a double bond. Now maybe you recognize that type of chemistry. That's an elimination reaction. And what are we eliminating? Maybe you could guess. We're eliminating a water. Now when we do that, we take away an alcohol, you make a double bond, but think about what is underneath that phosphate. Remember, this group right here is a phosphoester. That means that's a phosphate attached to an alcohol. And now, it is a phosphoester, but it's a very special phosphoester because that alcohol is not a normal alcohol. That alcohol is buried under there, and it's attached to a carbon that's part of a double bond. Actually, what that means is this is not a regular phosphoester, it's an enol phosphate. A phosphate attached to an alcohol that's right on a double bond. Now, you may remember that enol phosphate was way up at the top of our currency chart. So, look at what we've done. Again, we took something that's not worth that much. This is about 15 kilojoules per mole. We took away a water, and all of a sudden we have something that's, do you remember? 60 kilojoules per mole. We're going to spend that in the next reaction, but for now, we just got to sew up this one. Elimination of water is a lytic reaction. And what do we need to say here? The thing that we need to point out is we form an enol phosphate. And just maybe it's worth writing down. That's worth a lot. Have we added any ATP? Have we lost any ATP? No. The answer is no. That means we're still at break even. If we're going to make a profit on our ATP, we're going to have to do it in the next reaction. Let's move on and see what that's all about. Pyruvate kinase. Well, we know what kinases are, right? Kinases are going to be transferring phosphates from one molecule to another. We're going to start with what we finished with in the last one, phosphoenol pyruvate, or what we just call PEP. And we're going to do what we did last time we had a really energy-rich molecule. We're going to make an ATP. So we're going to take phosphoenol pyruvate with its energy-rich phosphate, and we're going to transfer that phosphate to an ADP to make ATP, and we end up breaking that phosphate off, and we end up with something that's called enol pyruvate. Now, we mentioned this way back in our last chapter. We said that enol pyruvates are not stable, and they are going to spontaneously, make a note of that, spontaneously rearrange in a very much downhill direction to a ketone. An enol becomes a ketone, and this ketone is called pyruvate. That's its whole name. I just put the keto there to remind you that that's the new functional group. The name is pyruvate. That's the final molecule in glycolysis. So let's pick it apart. When we break an enol phosphate, we have negative 60 kilojoules per mole if we go all the way over here to pyruvate. And when we create an ATP, phosphoanhydride, that's plus 30 kilojoules per mole. Once again, we can see that we are creating what we want, which is ATP, in a favorable fashion by breaking something that is worth even more. So this is a tricky reaction. It's got two parts to it. Let's summarize everything. This is a group transfer. All kinases are always group transfers. This is a named kinase, or PK. It's named a kinase because it's named after the reverse reaction, again, where we would reverse this, theoretically, take pyruvate and use ATP to put a phosphate on it. That is actually so hard to do that we don't do it in the body, but the name seems to have stuck. Let's go ahead and summarize this by saying that there's overall negative 30 kilojoules per mole. And we can just put down here that we're breaking an EP, and we are making a PA, and you can do the math on that. We got the negative 60 and a positive 30 makes negative 30 kilojoules per mole. Do you know how many ATP we now have? Well, we just gained one, but remember, we do everything twice at this point. So there we are. Our goal for all of glycolysis was to make 2 ATP quickly, and well, we didn't do it quickly on paper, but there it is. We made our 2 ATP through 10 reactions. Let's go back and summarize everything on here. Okay, back to our big picture. We look at our first energy investment phase where we put the 2 ATP in. Let's go down now and do our energy dividend phase. I want you to take a pen and go through and put everywhere you create an ATP. Use this style right here with an arrow and all that, but put it on there everywhere you make one, and we'll count up the net production of ATP. This is really worth pausing and doing. It's a big picture question. Okay, let's talk about doing this in reaction 7, where we take an ADP and make an ATP. Notice it's backwards. Up here it was ATP to ADP because it's an investment. Down here we're making an ATP, and it's a dividend. However, we've got to do this twice because reaction 7 happens twice. So this is where we were -1, -2, then we gain +2 there to get us to 0, and then we're going to do it down here as well in the 10th reaction. ADP to ATP, do it twice on both sides. ADP to ATP, that gets us our +2. So overall, 2 invested, 4 gained, net 2. And we also are going to make some NADH here. That's worth doing as well. That's going to happen in reaction 6. And we'll go ahead and fill those in there. Remember, NAD plus going to NADH is the creation of really good energy currency as well. That's 10 minutes. We'll finish it here.